Good morning to one and all, and welcome to the webinar on metal fatigue analysis using ANSYS nCode DesignLife. Just to give a brief introduction about the fatigue. The fatigue is the term which is borrowed from the human reaction of the tiredness due to repetitive works. Because if somebody has been asked to do the same kind of work repeatedly, so you'll be getting bored up at doing the same thing. So the same is being expressed as fatigue, whereas the same terminology when it is been adopted to materials. So materials which are subjected to repeated, fluctuating, alternating cyclic load tends to develop a peculiar characteristic behavior which differs fundamentally in certain respect from their usual behavior under static loading. This unusual behavior due to the cyclic loading in the material is called as the fatigue. So here we have specified that the loads are being repeated, fluctuating, alternating cycle. So when I say repeated, it may be the same load which is being repeating. Let us take an example that a tensile load which has been acting from 0 to 50 Newton and again coming back to 0 and again going back to 50. That is called as a repeated loading. Whereas when you describe it as a fluctuating load, that type of load which we are going to consider is going to be initially, it starts from 0, reaches to a specific value of tensile loading. Let us take about 20 Newtons. And again, it is going to be subjected to a compressive loading of 10 Newton. That means the sense of loading is going to be changed after a certain duration of time. And if this is going to be repeating, you call such a load as fluctuating load. Whereas we also define it as an alternating cycle. That means here the magnitude of the sense of loading are going to be having the same value. That means initially it starts from 0, goes back to tensile load of 20 Newtons and again comes back to a compressive load of 20 Newton and back to 0. So this cyclic loading, which is having the same magnitude but reverse sign, you call this to be as alternating cyclic load. And for all calculation purpose and the empirical relations which are being derived is going to be based on this alternating cyclic load. That means it is going to be subjected to a same magnitude, but of different sense in one cycle. So based on this, how exactly the material is going to be behaving and the corresponding mathematical relations are being derived. So the fatigue is a weakening of a material that caused by the repeated applied load, and it is a progressive and localized structural damage that occurs when the material is subjected to cyclic loading. So as we decided that the material which is going to be behaving in a peculiar manner when it is static loading. So when it is being subjected to cyclic loading, even the loads are going to cause the stress within elastic limit. The member has the tendency for the failure due to the fatigue. That is because of this peculiar behavior of the material. As per the ASME standard, fatigue is a general term used to describe the behavior of the material under a repeated cycle of stress or strain, which causes a deterioration of the material that results in the progressive fracture. So when we say fracture which is resulting from fatigue are among the most difficult to foresee because of the condition producing the fatigue are frequently not clearly recognizable. But inside the material, there may be the initiation of the crack due to the fatigue, and hence it is not going to be easy for identifying where exactly the deterioration takes place in the material. Then we define the fatigue strength. It is the stress required to cause the failure by fatigue in a given number of cycles. So at what level of stress, when you induce the member is going to fail for how many number of cycles. So the stress which is going to be induced for that particular number of cycle is what called as the fatigue strength of the material. And it is a quantitative relation between the stress range and the number of cycles to the fatigue failure. Then we have the fatigue limit or the endurance limit, which is going to be one of the property of the material. The stress below which the material never fails, no matter how large the number of cycles, then it will never fail at all. Such a type of material in which it is induced a stress level where for any number of cycles, the material does not fail. And the value of that particular value of the stress is called as the fatigue limit or the endurance limit. So such materials, we call it as the material which is going to be resisting to fatigue for infinite life. And that is going to be one of the property of the material for all calculation purposes which are available in the standard data handbook for any calculations which we try to perform for the fatigue life. Now, fatigue life is defined as the number of cycle of a specified stress loading characters. It may be repeated, fluctuating, or alternating. But the standard data which are available for different material, the fatigue life is based on the alternating cyclic load that the material can sustain before failure occurs at a specified nature. Now, in most cases, the fatigue life is calculated as the number of cycles that a member or a part or a material can sustain a specified stress before the failure occurs. That is going to be the number of cycles permitted at a specified stress before the material fails by fatigue. That means you have a specific value of the stress, then calculate for how many number of cycles it is going to consider before it fails. And that you call it as the number of cycles which it can sustain for a specified value of the stress is what called as the fatigue life of the member. Some of the notations and symbols or abbreviations which are being used in the fatigue life or the fatigue analysis. We know that usually in the conventional method of design or in any mechanical systems, the stresses are being abbreviated in terms of sigma for the normal stress and tau for the shear stress. Now, to make it a difference from the fatigue analysis parameters, in fatigue, we try to represent the stress in terms of S. Here, we try to define what we call it as the mean stress, on which is the superposed of oscillating stresses, SM, which is going to be representing sigma mean, which is nothing but the average of the sum of the maximum and the minimum stress. Then the stress amplitude is the amplitude of the superposed oscillating stress, has been defined as SA, which is nothing but the difference between the maximum and the mean value, or it is going to be equal to the average difference between the maximum and the minimum stress induced in the component. Then the stress range, abbreviated as SR, it is the difference between the maximum and the minimum. That is going to be equal to the twice the stress amplitude. Then we also use the terminology in most of the empirical relations defined as stress ratio. And the stress ratio is nothing but the ratio of the minimum stress to that of the maximum stress. And then we have the amplitude ratio, which is nothing but the ratio of the stress amplitude to the mean stress. Now, with these notations, as I discussed in the beginning, when we say fatigue loading, we have different types of loading, that is a repeated load, fluctuating load, and alternating cyclic load. So in the repeated load, you can observe here that it is going to be causing a test.
Hello.
Hello.
Yeah, sir. Are you speaking, sir, or just halted for some time?
Yeah.
Sir, can I ask you a question, please? Quick question.
Yeah.
Yeah, in your first slide, you said that a peculiar behavior of the material is observed What exactly that peculiar, why you are saying it's a peculiar
That
characteristic?
we'll be discussing later.
Okay.
Okay, peculiar behavior in the sense it is going to be at the atomic level. How exactly it is going to be behaving.
Okay.
Okay.
Yeah.
So here when we are trying to represent the repeated load, it is going to be either subjected to only tensile loading or the compression loading, but there is a variation in the magnitude. Such a type of loading, you call it as a repeated load, in which we'll be observing that the stress ratio is going to be varying between 0 to +1. Whereas in the case of fluctuating load, we have the sense of loading changing from one case to the other case, as for some time it is going to be subjected to tensile and for some other period it is going to be subjected to compression. So in which it is going to be having the stress ratio which is varying between -1 and 0. Whereas in the case of alternating cyclic load, we have that the stress ratio is always going to be equal to 1 because the magnitude of the loading or the stresses which are induced in the material is going to be having the same magnitude but different sense. And here one can observe that the mean stress for the repeated load is going to be non-zero. It may be either positive or negative depending upon the sense of load which has been acting on the member. Again, in the case of fluctuating load, the mean stress is always going to be non-zero. Again, it depends upon the magnitude of the tensile and the compressive stress, where it can be either positive or negative. Whereas in the case of alternating cyclic load, it is always going to be 0, that is the mean stress. And hence here you can see that the alternating cyclic load is going to be the simplified load, which can be taken mathematically equivalent to the sinusoidal wave behavior of the loading. So therefore, most of the case in the dynamics, we try to consider the loading to be harmonic, and that too specifically simple harmonic. Then in such case, the loading behavior is going to be sinusoidally varying, and that's the reason. So even in the fatigue calculations, we take this alternating cyclic load as the standard loads for all calculation purpose, and the standard values which are being determined and available in the data handbooks are being based on alternating cyclic load, whether it may be for defining the endurance limit or for defining the number of cycles or defining the variation of the stress and the number of cycles to failure, which we call it as SN curve, or the strain number of cycles curve, that is EN curve. All these things are being based on alternating cyclic load. Here, the mechanism of fatigue is being classified under 3 main headings. One is in the metal and alloys, we see that there is a localized changes in the atomic structures, which begins within the very first few cycle at a scattered point in the material. This is what the peculiar behavior, whereas in the static loading, it is not going to be changing the localized atomic structures. In the static loading, it is going to be distributed among the atoms, and then all the atoms try to resist the loading. Whereas in the case of fatigue loading, the way the stress distribution across the thickness are going to be different, and thereby the weakest atom is going to be behaving in a different way when compared to the strongest atom. And this weakest atom is prone for the initiation of the crack. Then these soon develops into a submicroscopic cracks, which grows as the cycle loading continues. And finally, when the crack grows to some critical size, at which the remaining of the material cross-section area cannot resist the given loading condition, the member breaks. So these 3 stages of the fatigue is referred as the nucleation or the crack initiation, and then the crack growth, and then the fracture. So here to describe this, initially, we have the first figure A, in which we see that there is a atomic or the grain which is very close to the boundary, which is the weakest one, because the inner grains may be having the adjacent atoms and it may be strong, but the grains or the atoms which are nearer to the surface are prone for the weakest atom. So at this particular atom, as the loading is going to be cyclically loaded, so the bond between thus, due to the frictional resistance, there may be some slippage occurring between the bond. And this slippage is been causing the orientations of the grain structures and other things in a different fashion. Now, as the loading increases, this slip planes keeps on increasing. And we can see here some of the slip planes which are protruding outside, and some of the slip planes are intruding inside. That means these slip planes which are protruding out are called as extruders, and these planes which are inside the materials are called as intruders. And these intruders planes makes the cross-section area of the member to be minimum. And that is going to be again the weakest plane which it can resist the loading. And this is the plane at which the initiation of the crack is going to be starting, which is being shown in this figure, where you have at many different planes, there is the slipping, whereas the weakest plane at which the slip is going to be more, that is where the initiation of the crack starts. And then in the second stage, the crack tends to grow. And in the third stage, when it cannot resist, it is going to be fading. Now here you can see that the initial initiation of the crack is going to be taking some time. And the growing of the crack is going to be taking some time, which are going to be slow. And hence the behavior of the material in the first and the second state, that is at the nucleation and at the crack growing stage, the behavior is going to be ductile behavior. And you can see in the sketches and also some of the components which are being experimentally carried out and shown as the photographs. These are having the very fine grain structure in which the behavior up till it reaches a critical crack is going to be ductile failure. And as soon as reaches a critical length of the crack, then it is going to cause the brittle failure. And this is being shown here. The grains or the initiation of the crack and the crack propagations will be slow and is going to be behaving as though it is a ductile material. But once it has reaches a critical crack length, then sudden rupture occurs, which is going to be brittle in nature. Then knowing this, to study the behavior of the material, one should know how exactly the stresses which is going to be induced in the member is going to be varying as the number of cycles are being increased. And from this, one will be getting that when the members are being loaded at different stress levels, how many number of cycles it can sustain. That is, what is going to be the number of cycles which the material can sustain for a specified value of stress is what important. So for every material, when it is being subjected to a specific value of stress, you will be getting a specific value of number of cycles. Like that, for when the member is being subjected to different stress conditions, we get the different life of the member. And the plot which is going to be plotted for the level of the stress which is induced in the member to that of the number of cycles which it can sustain is called as the endurance curve or the endurance graph. Our endurance curves are the graph showing the applied stress amplitude as a function of the number of reverse cycles to failure to fatigue. These curves are also being known as the inventor of this curve, Euler's, and these are also being defined as the Euler's curve. The most common procedure for generating the stress to number of cycles data is the rotating bending test. Now, this test uses the 4-point bending test, which is going to be considered to be as a simple member is going to be subjected to uniform bending. So thus, the specimen is being assumed, whatever which is being considered for the testing is assumed to be defect-free at this phase. And the stresses which is going to be induced in the member is going to be calculated based on the elastic beam theory given by the beam equation, where the stress induced is going to be equal to the moment which it causes or induces the stress into the distance of the outermost fiber from the neutral axis divided by the inertia, that is the area moment of inertia I. Now, these SN curves or the endurance curves are plotted with the cycles to failure on the horizontal axis and the stress amplitude on the vertical axis. Since the number of cycles which you are going to consider is going to be sometimes going beyond millions of number of cycles. In the conventional graph, when we try to plot that, it is going to be a too cumbersome process. Instead of that, we try to plot in terms of logarithmic scale, so that large amount of data can be shown on the graph using the logarithmic scale. And thus, the SN curve represents the mean stress data, that is the stress to the number of cycle test data, are usually presented on a logarithmic scale. And the stress-like relationship, which is going to be approximated as a straight line over a large range of endurance. Yes, even though the curve which you are going to obtain in the actual case, it may be of a different variation, but when it is converted into logarithmic scale, can be converted to be as a linear variation. Thus, the SN curve is obtained by conducting several rotating bending fatigue tests. Now, the specimen is loaded to create a certain level of stress and rotated until it fractures, so that you'll be getting one particular data. Like that, number of tests has to be conducted. Now, when the specimen fractures, the level of stress applied S and the number of cycles to fractures are noted, and this will give you 1 point on the curve. Here you can see that the standard specimen which is being used is the circular specimen of a specific diameter, which is being mounted on 2 bearing house, and this is being put onto the loading fixture, which is being loaded in such a way that it is going to cause a pure bending within the gauge length of the member. And this is being connected with a flexible coupling, which in turn is connected to the high-speed motor, which can be used for conducting the experiment. And along with that, you have the counter, which is being giving us the number of rotations the motor is going to be running. Now, the setup is being done in such a way that the circuit is being linked to the counter. And as soon as the specimen breaks, the motor stops, and thereby the number of cycles which it has taken is also going to be counted for. Now, the results of the test are represented by a point on this curve. Test at different stress level from ultimate strength down to a very low stress value with the corresponding cycle to fracture creates multiples of test points for constructing the SN curve. Now, the stress where the curve becomes asymptotic or horizontal line is determined as the endurance strength of the material. So here you can observe that most of the metals it is going to be subjected to the fatigue loading is going to be behaving in this particular fashion, in which we see that initially when it is being subjected to an ultimate tensile strength and up to the yield stress most of the time, or sometimes at point times the ultimate strength of the material is going to be behaving in a systematic manner in which it has a specific slope. So after reaching a specific value of the stress level, and that is going to be behaving with a different slope. And then after reaching to a specific value where the material is subjected to a stress level which is less than this, is we will be observing that the number of cycles are going to be the same. That means it is going to be having infinite life. Now, the value at which you have the asymptotic line, that is the curve which is going to be parallel to the horizontal axis, and that is the location at which the stress is considered to be as the endurance limit or the endurance strength of the material. Now here we have two slopes. In the very first instant, when it is being subjected to a high stress value, where it started from the ultimate strength to a 0.8 times ultimate strength, or usually and sometimes we'll also treating that up till the yield stress. The metal behavior is going to be different, having a different slope, and that particular region you call that to be as low cycle fatigue. Or in a standardized sense, we observe that any material which is going to be failing before 1,000 number of cycles, before 1,000 number of cycles, we call such a type of behavior as a low cycle fatigue behavior. So any material which is going to be sustaining more than 1,000 number of cycles, but within 10 raised to the power of 6 number of cycles, that is nearly about 10 million cycles. So if it is going to be within that range, then we define the behavior of the material to be as a high cycle fatigue. So anything which is going to be more than 10 raised to the power of 6 number of cycles is being called as material which has infinite life. So up till 10 number of 6 number of cycles, or 10 to the power of 7 number of cycles. Nowadays, everybody expects a little bit more. That is up till 10 raised to the power of 7 cycles, 10 raised to the power of 7 cycles to be as the limit at which the endurance strength is considered. Up till that, you call that to be as a finite life. Anything which is going to be sustaining more than that is going to be infinite life. Now, in the finite life, where the number of cycles is going to be less than 10 raised to the power of 6, can be bifurcated into two types. One is the low cycle fatigue, which has a number of cycles less than 1,000 number of cycles. The other one is between 1,000 to 10 raised to the power of 6 number of cycles. We call that as high cycle fatigue. Anything which is going to be sustaining more than 10 raised to the power of 6 cycles, we call it as infinite life. Thus, here the fatigue is considered as a high cycle when the peak stress in the material are held within elastic limit, while the low cycle fatigue occurs when the stresses are above elastic limit. So again, here the low cycle fatigue will be treated in a different manner, and the high cycle fatigue will be treated in a different manner, which we'll be discussing in the later on stage. Now, the mathematical representation of the SN curve, as we have classified as a low cycle and high cycle fatigue region, which is been bifurcating by, which is going to be varying from material to material, depending upon the tensile properties of the material. So the main interest in the engineering design is for a high cycle region, that is SN curve, which is being treated in the high cycle region, where the member is being subjected to the stress level within elastic limit. However, the low cycle fatigue can be advantageous only when a short life is required. Now, cycles of 10 raised to the power of 0 refers to the ultimate tensile strength. That is the stress value, which is equal to the ultimate tensile strength, while the endurance strength, SE, is taken to be as 0.5 times the ultimate strength of the material, which is going to be usually sustaining a number of cycles which is equal to 10 raised to the power of 6 cycle. Now, the stress amplitude is about 0.8 times the ultimate strength by which the high cycle fatigue starts. That is, when the stresses are going to be within elastic limit, then the high cycle fatigue is going to be start. Thereby, the correlation between the stress and the number of cycles in the high cycle fatigue, a region where the number of cycles is greater than 10 raised to the power of 3 and less than 10 raised to the power of 6, can be obtained, which are being derived by the mathematical equations, which gives you the equation of a straight line. Y is equal to mx plus c. And the same thing, replacing y by the stress and x by the number of cycles, one can write this to be as s is equal to m into n plus c. Now, considering the logarithm, This can be expressed as log of S equal to M into log N plus C, or S is equal to 10 raised to the power of C into N raised to the power of M, or the number of cycles which the material can sustain can be obtained as 10 raised to the power of minus C by M into S to the power of 1 by M, where M is the slope of the curve in the high cycle fatigue region given by minus of 1 by 3 into log of 0.8 of ultimate tensile strength to the endurance strength. And C is the intercept of the high cycle fatigue curve with the vertical axis. And that is being found to be a log of 0.8 of ultimate tensile strength square divided by the endurance strength of the material. Now, there are four major factors that affects the fatigue life of the component or a part. Those are the loading and the loading cycle or the cyclic stress state. And the second is the surface condition. And the third one is the design consideration. And then the natural environment which causes the fatigue life to deteriorate. Now, depending upon the complexity of the geometry and the loading, one or more properties of the stress state need to be considered, such as the stress amplitude or the mean stress or the range of stress, the stress ratio, or the way in which the stresses are acting as a uniaxial or biaxial or multi-axial, or the stresses, if it is multi-axial, whether it is in phase or out of phase, or whether it is going to cause some shear stress, and the way in which the loadings are being acting, the sequence of loading. All these things are going to be affecting the fatigue life of the component. Now here we treat the load factor affecting the fatigue life are, one is the maximum tensile stress of sufficiently high value, and if there is a large amount of variation or fluctuation in the applied stresses, or a sufficiently large number of cycles of the applied stresses. So here we see these effects when we are trying to plot the stress amplitude to the number of cycles, where the mean stress is going to be playing the key role, because we see that whenever the loading is going to be alternating load, the mean stress is 0, whereas other two cases where it is going to be fluctuating load or alternating load, then in such cases it is going to be having a non-zero mean stress. Now the mean stress, when we take that, if M3 is going to be greater than M2 and M2 is going to be greater than M1, that means M1 is going to be minimum, M2 intermediate, and M3 is higher value. And when you have the mean stress when it is plotted versus the stress amplitude to the number of cycles, and you can observe that here, for the same value of the stress amplitude, let us assume that if the stress amplitude is of 150 megapascal, and we can see that when the mean stress is of M3, sigma M3, the life which you are going to get is going to be 1 to the power of 10 6 or 7. Whereas for the same stress, if the mean stress is equal to sigma M2, the life is increased. Or if the mean stress is further less than M2, for the same stress level, the life is going to be different value. So this is how the fatigue life, which is going to have the effect, which is mainly depending on the value of the mean stress. And again, the type of loading, one can see that if the mean stress is of tension in nature, the stress amplitude to the number of cycles is going to be very less. If the mean stress is going to be 0, whereas when the mean stress is compressive, it has an advantage. Now you can see that at a specific value of the stress amplitude, we have 3 different failure values, in which when the mean stress is tension, that gives you a less number of cycles. When the mean stress is 0, it is intermediate. And when the mean stress is compressive, it is going to be giving a high cycle for failure. So that's the reason, one of the advantage of having the are inducing a residual compressive stress in the member as an advantage for the fatigue life of the component. And we see nowadays lot of research which is going on for inducing the compressive residual stress in the component so as to enhance the fatigue life of the component. From this figure, one can see that how when it is the mean stress is going to be compression, the fatigue life is being increased. Then based on the surface condition, how the fatigue life is going to have an effect. The first is the surface condition hardness. Hardness of the surface are enhanced by the heat treatment process, but should avoid stress concentration due to the heat treatment. Then the roughness. So how rough this or how smooth the surface is, because we have seen that almost most of the components when it is been subjected to fatigue load, it is at the outermost surface, the weakest grains or the weakest atoms are being prone for the initiation of the crack. And thereby, the roughness is going to be playing the key role in the fatigue life of the component. So fatigue life of a structure is highly dependent on the surface quality. And there is a quantitative relation between the surface roughness and the fatigue life. And then on the surface, the residual stresses, which can be beneficial or determinantal, depending upon whether the stress is compressive or tensile. If it is compressive, it is beneficial. If it is tensile, it is going to be determinant. That means if a tensile residual stresses induced in the component, then the life of the component can be expected to be very low, or it is going to be less. If it is subjected to residual compressive stress, one can enhance the fatigue life of the component. Then the material type, when we consider the design consideration, as we all know that in the design, the first and the foremost thing which you look at the selection of the material. So under the selection of the material, again, we try to see that how the grain structures and the distributions, and is there any defects in that, all those things are to be looked upon. And then in the design aspect, when we look at how exactly the geometry of the member has to be designed, such that as far as possible, one has to avoid sharp corners or notches. Try to provide certain fillets and instead of sharp corners. And thereby, by providing the geometrical descriptions appropriately without any sharp corners or notches, and by providing the fillet, one can enhance the fatigue life of the component. And also in the design consideration, one has to look about the environmental condition which causes the corrosion, erosion, or embrittlement, which is having an effect on the fatigue life. Then again, the temperature of the working environment, because extreme high or low temperature can decrease the fatigue strength. As we all know that the thermal fatigue occurs when the metal is subjected to high or low temperature variation. There is a fluctuation in the temperature, which usually called as thermal loading. And that is going to be called as a thermal fatigue. And this thermal fatigue conditions enhances or has the effect on the fatigue life of the component. So for taking into consideration all these things, one has to see how the endurance curve or the fatigue limit or the endurance limit can be modified, because the SN curve, whatever which we have drawn, is going to be for an ideal condition which is available in the standards. But if all these factors which affects the fatigue life is also taken into account, then in such case we have to see how how it is going to be different from that of the standard SN curve. So most commonly used specimen for fatigue analysis test in the laboratory are the rotating beam specimen, which are prepared very carefully and tested very closely controlled condition. Now it is unrealistic to expect the same endurance limit of an actual mechanical or a structural member to match the result determined in the laboratory. So here we see that we cannot say that always it is going to be of the standard specimens. The components are going to have a different shape, different materials, all those things. So some of the things which are to be considered is material, whether the composition is going to be similar to that of the standard test specimen, which is going to be the basics for the failure and the variability involved in the material, how the material is going to be behaving, all those things, and the way in which the product is manufactured, the method which is been adopted for manufacturing, the heat treatment which is being given, and the wetting, corrosion, surface conditions, and stress concentration which is being causing during the manufacturing has to be taken into account to make some modifications in the fatigue life of the component. Not only that, even the environments which has an effect on the corrosion and which is going to be causing due to the chemical effect, or if there is a variation in the temperature, the behavior of the material is going to be totally different. And the way in which the stress states, conditions, and the relaxation time for the stress relaxation and other things, as in the case of creep, where a constant stress which is being acting for a long duration of time may also cause the failure in the component. So these things should also be taken into account when it comes to the design aspects of the size, the shape, the life, stress state, the stress concentration, and the speed, that is the rate at which the loading is being occurred. And if there is any friction between the parts, those things are to be taken into account. And these factors are to be incorporated into the behavior of the material. So for all these conditions, Marin identified the factors that quantify the effect of surface conditions, size, loading, temperature, and other miscellaneous items. So the most prominence given to the fatigue testing was to gain an empirical understanding of the effect of various factors on the baseline standard SN curves, which are available in the data handbooks for most of the standards material. So if for any other materials other than the standards, then one has to look into these aspects. So Marin equation is therefore written for the fatigue limit of a machine parts as the endurance strength SE is going to be KE, KB, KC, KD, KE, KF into SE dash, where KA, KB, KC, KD, KF are going to be the modification factors due to various reached conditions. And SE dash is nothing but the endurance strength of that particular material under the standard specimen for the rotating bending fatigue limit. Now, Ka is the surface condition modification factor, Kb is the size modification factor, Kc is the load modification factor, Kd is the temperature modification factor, Ke is the reliability factor, Kf is the miscellaneous modification factor. Now, when the endurance tests of the parts are not available, then the estimation of the life of the component can be made by using the Marin factors to predict the endurance limit of the component. Now, let us take one by one the effect of surface finish factor Ke. Now, the surface modification factor Ka depends on the quality of the finish of the actual part and on the tensile strength of the part material. Now, to quantify the expression of a common finish, a machine part or a grounded machine or a cold drawn or a hot rolled or a forged part. The coordinates of the data points were recaptured from a plot of endurance limit versus the ultimate tensile strength. And the data are being represented by Ka equal to A into Su to B, where Su2 is the minimum tensile strength, and A and B are the constants to be determined, which depends on the type of surface finish usually given in the standard data handbook. Thus, the size factor has been evaluated using 133 set of data points, and the results for the bending and torsions may be expressed as Kb is equal to 1.24 into D to the power of minus 0.107 for the members which is having the diameter of the specimen to be varying from 2.79 and less than 51 mm. Our Kb is going to be 1.51 into D to the power of minus of 0.157 for the diameter of the member which lies between 51 and 254 mm. And for the axial loading, no size effect is there, so Kb is taken to be as 1. So what do we do when the round bar is bending, is not rotating, or when the bar is considered to be non-circular cross sections are being used? Now, the approach to consider the effective dimensions D is obtained by equating the volume of the material which is being stressed at and above 95% of the maximum stress of the same volume in the rotating beam specimen. Now, when these two volumes are equated, their length cancels, and so that we consider only the area. Thus, for a rotating circular cross-section, 95% stress area in the area in a ring having an outer diameter D and an inside diameter of 0.95 diameter. So designating the 95% of the stress area as A equal to 0.95 sigma. Then we have the 95% area, which is going to be equal to pi into D square minus 0.95 D square by 4, and that is going to be equal to 0.0766 D square. Now, this equation also valid for a rotating hollow circular cross-section, not only bending. And this is for the standard specimen. Now, this you are going to take it and equate it to the equivalent area for another kind of specimen, which is not of circular shape, or which is not rotating, or which is not bending. So, for a non-rotating solid or a circular cross-section, the 95% stress area is twice the area outside of the two parallel chords having the spacing of 0.95 diameter, where D is the diameter. Now, using the exact computation, this gives you the 95% area stress-induced area as 0.01046 D square. Where the D in equation 1 and setting this equation 2 equal to each other and solving for D, we get the equivalent diameter equal to 0.37 times the diameter of the actual specimen which you are going to use. And this is what here it is being shown. If it is not solid, if it is a hollow. So when I have to look about the 95% area and what is the stress which is induced, we calculate this. And if it is going to be other than circular, let us say rectangular cross section, for which the cross section area is F into T, and the 95% of the maximum stress which is induced is going to be this. Now, using this, when you compare with the standard diameters, we get D is equal to 0.808 root of FT. So these dimensions can be taken for evaluating the factors affecting the size. Then the load factor. So when the fatigue tests are carried out with axial pull and push, or rotating, bending, and torsion loading, the endurance limit differs, because in the case of standard specimen, it is being subjected to rotating when bending both. Now, the ratio of the endurance limit ranges from 0.7 to 0.9. Thus, SC, that is axial, is going to be varying from 0.7 to 0.9 times the ultimate, that is the endurance limit of the standard testing specimen. And thus Kc becomes 0.85. Usually it has been taken as average for axial loading. Now, the ratio of the endurance limit for using torsion and rotating bending test range from 0.5 to 0.6. That is when you take it only for torsion. And it is going to be usually considered to be varying between 0.5 to 0.6 times the endurance limit, which is our standard for based on the standard testing. So the average value Kc is taken to be 0.59. Now, the average load factor for bending usually considered to be equal to 1. That is because of it is similar to that of the testing condition. Then the temperature factor Kd is going to be. So whenever the operating temperatures are below room temperatures, we find that the brittle fracture is the strong possibility, and that should be investigated first. But when the operating temperatures are higher than the room temperature, yielding should be investigated first, because the yielding strength drops rapidly with the temperature. So any thermal stress will also induce creep in the material when the operating temperature at high factor, so that these factors have to be taken into account. Now, defining the load factor Kd as a ratio of the strength of the operating temperature to the strength of the room temperature. Thus, Kd is equal to SUT divided by SURT. Thus, SCT, that is the endurance stress at the temperature, is going to be Kd into the endurance limit at the room temperature. Now, the reliability factor, AE, which is going to be based on a reference rate as from the standard specimen. And the estimation of the reliability factor is completely based on the assumptions that the scatter or approximated by the normal or the statistical probabilities density distribution. And KE is taken to be varying from 1 to 0.08 of ZA, where the value of ZA is associated with the various level of reliability, which can be found in the literature by Shigley and et al. So taking the miscellaneous effect, other than what all the things which you have not considered, all those things is taken as the factor, miscellaneous factor, which is KF, is intended to account for the reduction in the endurance limit due to all other effects. It is really intended that these must be accounted for because the actual value of KF are not always available, as in the case of stress concentration or non-sensitivity or residual stress, or when it is a metal row spring due to that the chemical effects or corrosion, or due to cyclic frequencies or electroplating, whatever it may be the case. Then this effect is going to be taken into account. So when we try to take all these factors and try to modify the SN curve, so the modified SN curve, which is being plotted for the stress amplitude versus the number of cycles to failure, is being taken into account. And you can see here, the endurance strength SC is going to be SC dash KA, KB, KC, KD, KE into KF. And this is the endurance strength after taking into all the factors into account. And this is going to always be a little bit lesser than the actual endurance strength of the material. Let us see how the fatigue life is going to be predicted. Now, the fatigue failure were developed to characterize the importance of fatigue cyclic loading, which is being caused in the right wheel load, which has been observed by Wohlers first. So he carried out an experiment for a rotating bending test on various alloys, and an empirical relations were being developed. And that is what we call it as the endurance curve, or also called as Wohlers curve. Now, the prediction of the fatigue life has an outstanding importance and must be considered during the first step of the design of any component or a part. The engineers have used many methods to determine the fatigue life of the material. Among them, the 4 methods are widely used in today's industry. One is the stress life method, or a total life, or which we call it as SN approach. Then the strain life method, or called as crack initiation, or EN approach. Then the third one is the crack growth method, which is also called as fatigue life prediction by fracture mechanics approach. And the fourth is the probabilistic method, which can be used on either life or the crack growth, or the combination of all these things. And the probabilistic way of predicting the fatigue life is the probabilistic method. So the stress life method, or the total life, or SN approach. The fatigue endurance curve, which relates the stress amplitude to the endurance, are generalized to make more widely applicable. So there are 3 main areas which is being generalized. Those are to allow the constant stress amplitude endurance curve to be used to analyze complex stress history, and then to allow the endurance curve drawn from a smooth surface test specimen to be used with a different shape of the component, or to allow the endurance curve established by testing one material to be used to calculate the fatigue life of another material, and if possible to estimate the life properties of the material without performing the fatigue test. So in these 3 ways, one can just consider the standard SN curve and try to implement for the analysis, or carrying out or predicting the fatigue life of the component. So in the stress life approach, the Wohlers curves which are being considered, and based on that, Baskin proposed a mathematical equation to represent the part of the SN curve, specifically in the high cycle fatigue region, where the number of cycles is more than 1000 cycle and less than 10 raised to the power 6 cycle. And that is being related as SR equal to A into N to the power B, where SR is the alternating reversing size stress, which will give the fatigue life of N cycles for greater than 1000 number of cycles and less than 10 raised to the power of 6 cycles, and A and B are the material constants which are to be determined. Now, taking the logarithms of these three equations, we get log of SR equal to log A plus B log N. Now, for a small number of stress reversal, let us say that when it is having the intermediate between the low cycle fatigue and the high cycle fatigue, where the number of cycle is taken to be as 1000 number of cycle, where we consider that to be equal to the stress level which is going to be induced in the component as 0.8 or 0.9 times the ultimate strength of the material. Thus, at n equal to 1000 number of cycle, SR is either 0.8 or 0.9. Here I have taken both the cases and substituted that value, and we will be getting for 0.9 times the ultimate strength this equation, or when it is 0.8, this is the equation for the stress induced and the number of cycles relating the constants A and B. Now we know that when the number of cycles is 10 raised to the power of 6 cycle, that is where the limit of the stress or the stress which is induced is called as the endurance stress. And substituting the endurance stress at that value, we get the expression as log of SC equal to log A plus of B into 10 raised to the power of log of 10 raised to the power of 6, or it is log SC into log A plus 6B. Now, while calculating these two and taking the previous equation and subtracting, one can get the constants A and B. So B is going to be given by this expression, and A is being by defining this expression. Now, knowing A and B and using the equation for the by the Basman SR equal to A into n power B, one can clearly plot the SN curve and also determine the number of cycles to failure occurs for the specified stress range, knowing A and B. This is how usually mathematically we calculate. So here we have taken the calculations for three different cases for bending, axial, and torsion. And we can see that the torsion is going to be giving us less, taking into effect all the factors. So the standard values which are being considered for the endurance stress are being specified. Similarly, for other materials, here we have specified to consider the endurance strength of the material which is going to be. Now, another thing which is going to be key in the stress life approach is the stress concentration. As we all know that the quantitative evidence for the stress concentration was first started with the Illing. Yeah.
Yeah, can you just go back to the previous slide, please?
These are all available in the standards.
Okay, I just want to ask you that, what is the for steel, what do you take the endurance strength correction that body based on the modification factors? So by what factor do you reduce the this factor 0.5 to SU is there, no? So there, how much is the factor you can consider by considering all those surface finish factors and all those factors which we discussed, no? So what is the value that you recommend here for steel?
No, that has to be looked upon, which is the factor which you are going to consider, and we discuss what is the value factors which you are going to take up. Each factor is going to, those things are to be incorporated here. Because and naturally, this is going to be reducing.
Yeah, so what is the recommendation value? Because 0.35 and all is too very conservative, which will generally not.
These are all the standards, and these are to be considered as the standards, and the factors which are affecting the fatigue lives are to be incorporated here. And then based on that, which factors are going to be prone and which is the most important, those are the factors which are to be taken into account. This is going to be varying from 10 to 20% variations will be there. Taking all the factors into account. On either side, 10 to 20%.
Okay, I have one more question for you. Okay.
Yeah.
So we derive the endurance stress by all those things. Like, we have some value for the endurance stress. Let us assume that we take it as a 0.4% of the ultimate strength and we get some factor there. And is it possible that a material will still have a finite life if the number of loadings, whatever you have, number of load is very high? We are having repeated loadings are very high, but the stress is below the endurance strength, whatever we have derived. Is it possible that the material can still have a finite life?
Yeah, definitely. Because it also depends on the magnitude of the stress induced in that and the way, the sequence in which it is going to be and the speed at which it is going to be acting.
No, no. What I mean to say is our stress is not very high, or it is below the endurance strength, whatever we have derived the endurance strength. Based on that,
Right.
it is the slight below that. Second thing is if the loading number of blocks that you have for the loading is very high, is it
Yes.
possible that this stress will get, you get a damage which is which will have finite number of life? That is what is my question. Is it
Yeah,
possible like
because
that?
because the endurance strength, whatever which is being given according to the standards, is being based on the alternating stress cycle and on a standard specimen. But in the actual situation, the specimen is not is what which you are testing. The actual component has a different geometry, different material, different loading conditions, all those things. So when you, even for a simple example, the loadings will never be always having the same amplitude. For some number of cycles, the loading is going to be having a specific range, and after a certain duration of time, the range may be changing. When the range changes, the behavior of the material is also going to be affecting the fatigue life.
Okay. Okay.
Because when we see that the third approach, that is the crack growth approach, in which we adopt the fracture mechanics approach. So in the fracture mechanics, the crack growth is depending on the previous load history. So previous cycle, how the load was. So whenever there is a change in the load history, then the variation in the stresses are going to be too critical.
Okay. Okay,
Because
we'll discuss that.
it is going to be a function of load history. That is one example which I am giving. And again, you cannot say that it is going to be always having the same amplitude in each and every cycle. So if the variations of the loading is random in nature, then we have to adopt the statistical methods to make it a narrow band of data which have to be calculated. For treating that number of cycles and the variable frequency amplitude curves, you have a separate this thing. We have to adopt that and then make it as a equivalent constant amplitude bands and then calculate the values. So all these things will have the effect, even though it is stress below the yield stress of the material, that is the endurance strength of the material.
Okay, okay. So that's what, because recently we came across one situation. Maybe I'll discuss with you separately on that.
Okay.
Yeah, yeah. Thank you.
So the notch effects is going to be very critical. So as we know that the stress concentration is what which is being considered in the statics design, whereas when it comes to when the loads are going to be cyclic, then we have to look into the stress concentration factor due to fatigue. So how we define the stress concentration in the static analysis, which is given the ratio of the maximum stress to nominal stress. Similarly, the fatigue loading factor, Kf, is defined as the peak stress to the nominal stress. So with this, we have the notch sensitivity effect Q defined by Kf minus 1 divided by Kt minus 1, where the notch effect is being taken into account here. And one can see that the notch factors Kf is going to be the stress which is going to be induced for the yield with a smooth specimen to that of the notch specimen. Based on that, one can determine what is going to be the value of the stress fatigue factor. And we have empirical relations which are being derived. So this relationship was being considered. And when one can get the what is going to be the fatigue concentration factor Kf. Then we have the strain life method, and this is being widely used for the low cycle fatigue. So where the high stresses are being induced in that. And Coffin and Mason were the first people who arrived at the effect of high stresses caused due to the thermal fatigue. And they developed the plastic stress strain relation. And they noted that the logarithm of the plastic strain amplitude, which has been plotted against the number of loading reversing cycle, relating the increment in the plastic strain relating to the number of cycles. Here you can see that how the variations are of the stress distribution, and there will be some amount of stress or the strain which is in the plastic zone and in the elastic zone. So the total amount of strain induced in that is going to be partially elastic and partially plastic, and these are being related, and then arrive at the stress to number of cycles curve, where we have the resultant SN curve which is being plotted by considering independently the elastic behavior and the plastic behavior. So the elastic behavior of the material is treated here, which is going to have the slope which is going to be equal to B, whereas the plastic behavior of the curve is being plotted here, which is going to be having the slope C. Now the resultant of this is going to be the actual behavior of the material in the highly stressed component treated under the strain increment as the strain approach. Here we can observe that in the region which is having the number of cycles less than NF, that is at which the interaction between the intersection of the elastic nature behavior and the plastic nature behavior is going to be within this, it is going to be the plastic state of strain is going to be causing mainly for the fatigue failure. Whereas anything which is going to be having the number of cycles greater than NF, beyond this, it is going to be the elastic portion of the strain, which is going to cause the fatigue failure. And the number of cycles per failure is related with the stress to strain and the X modulus with the constant, which are the slopes of this curve. Then in the fracture mechanics approach, it is going to be for the crack growth, because Paris was the first person who introduced the fracture mechanics and found to be as an useful tool for the fatigue crack growth. And since then, this fracture mechanics approach is being used to analyze the fatigue life of the component. The method and the procedure for the analysis of a constant amplitude fatigue under small scale yielding condition at the crack tips are fairly well established. But although the number of uncertainty remains, this is what here it is. The variable amplitude loading, large scale plasticity, short crack introduction, added complexity and not fully understood even today. Here, similitude, that means comparison between the two, the actual case and the predicted one, and the crack tips are going to be taken into account. So these things are being taken and then analyze this and see how exactly the presence of the constant amplitude stress cycle and the plastic zone, which is going to be developed at the tip of the cycle, is taken into account, in which you have the maximum stress intensity factor and the minimum stress intensity factor, and the rate at which the crack growth is given by dA by dN. And here it is going to be found that it is a function of the range of stress intensity factor and the ratio of the stress intensity factor. Now here when this is for a constant amplitude. If it is a variable amplitude, then the load history of the previous cycle is also going to be one of the function. Now if you assume that it has a constant amplitude for a constant amplitude cycle, then the number of cycles to failure is being taken by integrating this, and that can be determined to be as n is equal to the integral of dA by Fn of delta K into R within the limit from A0 to AF, where A0 is the initial crack length which is being developed and AF is the final crack length. So with this, one can determine how exactly the crack is going to be growing and when the failure is going to be occurring. Now, this is what you call it as a similitude curve, a typical fatigue crack growth behavior in which it has three regions, first region, second and third. The first and the third region are of not of much important. In the high cycle fatigue, it is the second region is more important. And based on this, we see that there is a linear variation. Straight line is there. And this is being used for the prediction of the fatigue life. Most of the empirical relations are based on this. So here I have listed some of them. Since time is getting short, I just go through this, the different laws and the different empirical relations for calculating the rate at which the crack growth with the number of cycles are being given specified. And among these equations, any one of those can be used depending upon the type of application and other things. So here all the equations are strictly valid only for constant amplitude loading. Now each of the equation 1 to 7 can be integrated to estimate the fatigue life of the component. And the most general is the fatigue crack growth model containing the material constant Cm, K critical and K threshold. So the threshold stress intensity factor range is again going to be another important in the predicting the fatigue life of the component by using the fracture mechanics approach. And also it depends on the ratio of the stress intensity factor, that is K minimum to K maximum. So any questions? Any questions?
Yeah, I think we can proceed further. Thanks to Dr.
Yeah.
Jagadish. There is a course on metal fatigue at virtual engineering. You can browse it through and then you can take up the course. We'll send you the details post this interaction. So moving forward, there are three different topics we'll be covering. One is just to introducing the DHIORESEARCH, and then we have metal fatigue analysis using ANSYS Mechanical as a standalone tool, and using nCode as an DesignLife as a special code for metal fatigue analysis. Okay. So myself, Santhosh, I'll just brief about the DHIORESEARCH thing in 5 minutes time. Then we will get into my colleague Aravind will demonstrate the how to calculate or the capabilities within ANSYS Mechanical Workbench with a fatigue tool. What are the facilities available and how to calculate the metal fatigue life within KSL. And then I will demonstrate a small workflow for encode DesignLife fatigue analysis part. Encode DesignLife has a lot of features and a lot of applications things. We will be coming out with subsequent webinars or the workshops in the future days to cover all of them. Today, we will cover most of the workflow pattern for it. So in continuation, we would like to introduce our company, which is DHIORESEARCH and Engineering Private Limited. It's a 12-year-old company, predominantly on analysis segments. So we work on structural mechanics, computational fluid dynamics, the manufacturing aspect, thermal hydraulic, material modeling and simulation, then the piping, pressure vessels, and so on. So about 40 people team, 11 consultants working in Bangalore. We have office in Rajajinagar, Bangalore. So major activity here is on the structural mechanics. If you look at, we work on all the complete range of the nonlinear FEM part, whether it is static to dynamic to linear to nonlinear to thermal, explicit, implicit. So that's our starting point for all the activity. And then we work on fatigue, durability, and fracture mechanics, and that's our core strength. Not just the metal fatigue, even we work on polymer fatigue, like assessing the life of elastomers, polymers, or it can be tire, rubber bush, or any of the elastomeric material. And in situ load measurement, because your standard equipment, standard operations, you will get the load from the standard handbook. or the measured part. But when it comes to off-road kind of vehicles and I think the load becomes a very critical. So or developing a duty cycle which is required for the metal fatigue or the fatigue evaluation, or followed by a fracture mechanics part. So we have been evaluated for various structural integrity assessment with RLA studies and so on. And we also go simulate manufacturing process simulation and computational fluid dynamics at a system level, component level, mesh-free method, and discrete element. Similarly, we characterize the material for different aspects from the atomic level to macro level of applications part, and for all the kind of mechanical and other equipments. We do a consulting R&D, sell some of the softwares which are very niche area applications based things. And then we also do a training activity where you can reach out to our virtual engineering. There are a lot of physics based as well as code based or software based training programs are happening. So this is our total solutions for the fatigue or structural integrity studies. Everything starts with an ANSYS space climb where you start modeling the CAD model or from the measured data from different segments, like for example, scan data or the lasers, different scale, the measured data. Once the CAD is prepared, then we move on to the like FEM preparation. We work with ANSYS, then also for other codes for the FEM evaluation. Then it comes to the fatigue. In the fatigue, there are three aspects which is majorly looked at. One is the material data, where we can test it and add it to the material data. The other one is a load curve. We work on True Load. True Load is a software developed by Wolfstar Technologies in US, which works very integrated way with Abacus, ANSYS, and other codes. And it can have a correlation between the physical measured data and simulated to develop a duty cycle for the fatigue and the load curve for the FEM part. In the metal fatigue, we work on nCode, and nCode is for the detailed metal fatigue evaluations. Different kind of fatigues it can evaluation it can handle, especially on the like weld fatigue, vibration fatigue, thermomechanical creep fatigue interactions. The other segments where the physics of the fatigue is getting changed. So that is capable of handling with the nCode DesignLife. We'll look into the basic introduction today and then subsequently on different physics. Then comes is the elastomer or rubber fatigue, where we work with Endurica. And Endurica is a very specialized code for handling the polymeric material fatigue, which is little different from the metal fatigue applications part. And then we move on to the next stage where the fatigue will definitely all of us know that it will handle up to the crack initiation, number of cycle for crack initiation. Once the crack is initiated, introducing the crack and further doing the fracture mechanics simulation, we work with Frank 3D. Frank 3D is a 3D crack growth simulation, works on M-integral based approach as well as the displacement correlation method or the J-integral based approach. We also have a probabilistic approach because Frank 3D is a more deterministic approach where you get the crack introduced and the crack propagation part, where the anomalies coming from the manufacturing and other aspects are not specifically handled. Which will go with an Darwin. Darwin is an SWI. I developed software, which is Southwest Research Institute developed software. All of this works with an ANSYS ecosystem and to handle from the conceptual design to up to the fracture or the failure applications. There's a partial list of customers we serve from defense to public sectors to OEMs, different OEMs, and around 800 plus customers we served in last 12 years. And also worked very closely with all the IITs and associated academic institutions on different physics solving and other aspects. This is our technical presence and publications where we have published paper with damage tolerance studies for remaining life of an turbine generator of hydro shaft with the CPRI as well as with IGCAR and ISC and the other organizations. I think a couple of you may be familiar with our conferences, which is coming in, which typically happens every year, but due to COVID after 2019, it is not there. 2024, it will be in the March, April time. The international conference where 500 to 600 people attend, and there will be an expert joining, and Springer is being our publishing partners. And we also have very dedicated training programs keep on conducting, and you can just please be part of the things. We'll share the detail studies for the different. This is the overnight failed structure of a reclaimer. And similarly, we have executed around 300 projects, more than 300 projects, because our area of application is very niche and we are only into the analysis segment. This is just to introduce our company into the things. We have been working in fatigue and fracture for quite some time now. And uh, with this, I'll just ask my colleague, because of time short, we are just rushing through. My colleague Aravind to demonstrate the fatigue case, how to do it in ANSYS, and then we'll get into the encode part of it. Aravind, over to you.
Yes, sir. Thank you. Hello, everyone. Myself, Aravind. I'm working as application engineer at DHIORESEARCH and Engineering. Today, we can have a simple demonstration on universal joint and how to give the loadings and boundary condition for that, and including, and also we can see how can we estimate the fatigue life due to that load, and also damage and safety factors. Let's move into the
Share
simulation
the
part.
screen.
Yeah, I think my screen is visible.
Yes.
Yeah. This is actually the GUI of the workbench, where you can see on the left of the screen, you can see the various types of analysis. For each of these, we can perform the fatigue life analysis. Let's say in static analysis, we can perform the fatigue life. In some cases, due to the varying load with respect to time, like transient analysis. Uh, in transient analysis also we can perform the fatigue life, and in some cases like vibrations and dynamic cases like random vibration, spectrum loading, and those things also we can perform the fatigue life. And in some cases, due to the friction, there is a generation of heat due to the friction between the components. In that case, we are going to use this coupled field transient analysis. There we are merging between the transient structural part and with the thermal part. There we can perform the fatigue life. The first and the foremost thing, we need to have the material details to estimate uh, the fatigue life. Let's say we need to, for the first thing, we need to drag and drop this structural part or whatever the analysis you are performing. And then the stepwise procedure, like we need to include the material data, and we need to include import the geometry, and then comes the boundary condition and loading, then the post processing things. Let's move into engineering data. For the default, we have the structural steel in ANSYS. Let's take the structural steel for this case, and then we need the basic inputs like density, and the isentropic elastic Young's modulus and the Poisson's ratio. Based on this Young's modulus and Poisson's ratio, the software will calculate the bulk modulus and the shear modulus. And then we need the SN curve. Uh, the SN curve can be inputted in 2-3 ways, like depending on the inputs, like what we have log scale. You can see on the right of the screen, you have the graph which is showing the number of cycles to the alternative cycles, which is in terms of log scales. If you have any semi-log scale, you can change this into semi-log scale. When you change it into semi-log scale, it's going to change one of the let's say cycles are in log scales, and this is in the 10 power 9 cycles. Depending on that, we can define them. And also linear scale, which in both are in a numerical unit wise. And then let's keep it in a log scale. And then if you this is an experimental data which we need to get it from the experiment data. So like we need to give the number of cycles versus alternating stress. It can be of like pascals or MPa. You can change it over here. Uh, you can change the parameters, sorry, the SI units, and then you can introduce the values into the engineering data. And then after this, you can see the graph of the SN curve. and you need to introduce input the yield strength and the ultimate strength. And let's say the SN curve is used only when we are performing the stress which is developed in a body which is less than the yield strength. In that case, we can perform the SN curve where when the yield strength when the material is subjected to a load which in produces or create the stress which is more than the yield strength. In that case, we need to perform the strain life parameter. This in this strain life parameter, we need to give these coefficient values like strength coefficient and exponential and ductility exponential and cycle strength and hardening exponential. These are the experimental datas we need to give from the experiment. And depending on that, as Jagdish sir has explained, you can see this. This is a plastic strain life, and this is a elastic strain life. Due to this combination of these two, we get this plastic total strain life curve. And then we need to import the geometry here. So this is a simple case. This is geometry which I am going to use now. This is a universal joint, and then after that we can move into meshing parts and boundary conditions. Let's say in geometry we need these are the parts which we have included, and we need to assign the material here. You can see the material which I am assigning as structural steel. And this is a step-by-step procedure we need to carry out. In this, the green tick marks indicate that this geometry is sufficient for the next step. In the same way, each step to be indicated with a green tick mark, or else it will show a question mark, which means we need to give some input data are missing. So in material details, you can check whether the given inputs material values are being correct or not. And then we can move into connections and the contacts we can define between the two parts, like connecting using contacts or joints, like revolute joints. I have defined between these two parts. I have defined the revolute joint. After that, we need to do some meshing. I have kept as a default meshing. We can have some refinement over the part which we have the more interest of estimating the life. And then when you come to the boundary conditions and loading, when you click on insert, we can have this boundary conditions at the bottom, and the tops are the loadings. And here I have introduced the moment for one of the end of the joint with the moment of 5 into 10 power 5 moment Newton per mm, and then one of the end is fixed support. The same moment will be transferred over this to this shaft. Due to this loading, we can get, when you solve this problem, we will get the total deformation and insert the total deformation and stress and strain values. And we can see the fatigue life tool here. When you insert this fatigue tool, we can estimate the life damage and equivalent alternative stress, and also the fatigue sensitivity. And this moment reaction is introduced by using the probe value. In this post processing, we can see the total deformation, and the equivalent stress is maximum over here. When you switch to maximum, it's showing somewhere here between the joints, between the two joints, like here about 141.56, which is less than the yield strength of the material. So we can get some number of cycles it can serve like this is a directional deformation in X, Y, and Z. And in the same way, we can get the principal stresses, maximum principal stress and the minimum principal stress. And when we come into the fatigue tool, we can see like as related to theoretical part, we have a fully reverse zero based and ratio, and this history data is like time dependent varying load we can input using history data. And zero based, when you click on zero based, it takes only the positive value of the stress, like only the tensile property, and the other end with zero stress. And in the same way, when you move in, when you click on fully reversed, you can see the both compressive and the tensile loading are being applied with a factor of 1. We can change the factors, like if you want to increase the load with uh, let's say having introduced the load with 5 into 10 power 5 Newton per mm. If you need to increase that loading, we can increase this safety scale factor over here. And then when you come into ratio, we can define the ratio between the tensile and compressive loads. Here it has taken as -1 and 1. We can change the values here so that you can see the tensile properties, whatever the stress 141.85 will be included. Half of it will be included for the compressive load. That is the factor we are going to use here. Let's keep it as a -1, that is equal. For that, we can go for a fully reversed life type, and then we can estimate at different time intervals. And we can go for a ductile material, we prefer for mean stress theory with Soderbergh, and we can estimate the units, the life in terms of cycles, hours, or seconds, or days, or month, and these are the outcomes we can get it from the simulation. And then I will go by fully reversed with a factor of 1 and with a Soderbergh equation. If you evaluate these things, life, you can see this blue indicates with a maximum life of 10 power 6 cycles, whereas the minimum life is over here. It is about 91,000 cycles we can perform with this loading. And you can see the damage is also maximum over here. Let's say I will clear this data. Let's say you can give the design life whatever you are expecting from this model. Like I have given like 10 power 6 cycles to be the service life of this component, so that what is the damage you can estimate. This is a damage value from this loading. And in the same way, for the fatigue sensitivity, we can get.
Excuse me, what is the damage you got? It should be lesser than 1, right?
Yeah,
You are getting 10.91 you are getting. So then how your life is 10,000 cycles?
no sir, like for the damage for this life cycle, if you for this let's say I will decrease this life cycle. If I decrease less than
No, no,
whatever the
first of
life,
all, no, no. What stress combination method you have used? You have taken maximum principle, right? You should for a ductile material, you're supposed to use
equivalent
1 minus.
stress,
Yeah, you should
equivalent
use 1
stress.
minus stress, right?
Yeah, 1 minus stress only I included, sir, like a stress component here, equivalent stress.
Okay, okay. Then why did you use Soderbergh? Usually Gerber method is preferred, right?
For,
Your Soderbergh is very conservative here.
yeah, for this example, I
You can
like
use any of them. The option is available there. So
I guess
yeah, sir, you can use the different stress theories. For this, I have considered like ductile material, so I used this Soderbergh. If
no, I was
I,
just
no,
yeah, tell me,
it
sir.
depends on your problem statement and also the material dependent. So
Yeah,
you can use the facility. The what he is demonstrating is you can use those equations and the
you can
how
use
to perform
different
the work.
stress
okay.
theories.
Now go to damage. What is the damage you are getting? I'm not. Oh, yeah, please run that. It's not updated. I think you update that.
Yeah, Sir, as you ask, because the life, the limiting, this can serve up to 91,000. Whereas in
What
the
is
damage,
your damage? You please show me damage.
in damage life, if I give less than the life, like 90,000 cycles, it will show less than 1. If we increase the number of cycles here, it's going to give the higher value of the damage.
No, thing is.
No, damage, see it's a target design life you are going to add it. And for the current one, you are getting about 94,000 is as a cycle. If you are adding below that, definitely the damage will be controlled below that only. So if you are adding, if you are expecting for, let's say 10 to the power 6, then the damage levels also goes high.
Yeah.
No. Thing is, the inverse of the damage would be the life that it gives, right?
Yeah, like damage is we have a formula for the damage, like whatever the life we are expecting, design life by total life.
The damage,
No,
whatever you are,
no,
you are getting here, that should be the inverse of your life, whatever you are, but it is not matching. That is what I'm saying. The 0.988 it's getting. How much life it can expect with 0.988?
Sir, if you calculate like damage is equal to the number of design life you are expecting, like I am expecting 90,000 cycles divided by whatever the life you are getting, 91,000 in 90,068. If you divide this design life by this total life, you will get the damage value, this 0.98. If I show, let's say, 1 second.
So damage is coming high. That is what is my.
No, damage is with, if it is within the cycle, failure cycle, then the damage is within one number, right? If the cycle you
Yeah.
are giving high, then the damage also need to be high, right? I mean,
Yes, sir. That's what.
Because what we are seeing here is below the 90,000 cycle. If you are giving 10 to the power 6, then it will be high, damage will also be high.
Sir, you can see the
Yeah.
damage value here. This is a life what we are expecting, 90,000. And then this is a life what we are getting from the simulation. If you divide these two things, we are getting the damage of 0.98. The same value we are getting like 0.9882. I think it's clarified.
Here,
Okay.
like there are two ways.
I will discuss it separately.
Two ways of looking at a cycle.
Yeah.
Can I? Okay. Okay, I'll just brief you. There are two ways of looking at. One is you subject the component for number of repeats and understand like how much life it can withstand. Okay. The second one is you expect the component, what will be the damage level within the my targeted cycles. So what design life option gives in ANSYS here is you can give a target cycle and see that whether there is a damage or whether the damage levels within that cycle. Else you can, if it is not, if the life cycle is not crossing, then the damage level also will be less than 1.
Yes, sir. That's right. Thank you, sir. And then if we come to fatigue sensitivity, here we can have a graph like this is a whatever the load we are applied, it's showing the number of alternating cycles with respect to this. As we decrease the loading, it's going to increase the number of cycles. This is what it's showing. And if we increase the number of the factor of loading, it's going to decrease the cycles. This is the fatigue sensitivity. And this is how we can calculate the fatigue life using ANSYS. And then we can move into like nCode. This will be demonstrated from by Santhosh sir. I will hand over to Santhosh sir.
Yeah, just to add here, ANSYS standalone tool can predict fatigue up to certain extent, and then specialized tool is a nCode part. Thanks, Aravind.
Thank you, sir.
Okay, so so ANSYS has two options for you to perform the fatigue life assessment part of it. One is ANSYS fatigue tool within the ANSYS Workbench, and in the enterprise editions you will get that fatigue evaluation. Also, premium edition you get. And the further detailed analysis of fatigue can be done with ANSYS nCode DesignLife. nCode DesignLife is a specialized product for the fatigue evaluation, where you want to account different loading patterns, different material models, and also the specialized data for the fatigue. So we all know, like typically what encode can give you is what are the parameters which will make an issue with, or will be contributing in terms of fatigue life calculations, that you can standardize your fatigue evaluation curves. So this is basically to help the designer in evaluating the fatigue life at a well in advance, and accounting the realistic load and material data into considerations. So I'll just skip all these things. So coming to here, so typically we will have a design, and then we prepare the FEM model, where you can take the material data, and then based on the material data as well as the loading conditions. The loading conditions, either you can do a cycle assigned in the FEM here and repeat in the fatigue, or you can assign a unit load and then make it in the fatigue. You can repeat by mapping the things. So that's where the duty cycle development and the combinations will come. So one is the load combination, the second one is the FEM results, and then material property from the fatigue side. And then combining all the things, we will get the fatigue contours. And also it will help you to redesign the by changing the geometry, you can rerun it. So when you are running a fatigue analysis independently, and when you are running fatigue analysis along with the ANSYS Workbench, whether it is ANSYS fatigue or ANSYS encode fatigue, the advantage is it will help you in the redesign quickly, because your geometry can be quickly optimized, or you can use the optimization package within the ANSYS encode, where you can change the geometry and take it to the fatigue and update the results in the fatigue. You will be able to see that what is the influence of your change in geometry is contributing to the fatigue life. Whereas in other cases, what happens is, if you are looking at a FEM done separately and then import it, this is a continuously you have to do this activity. It cannot be automated. Whereas in the encode using within ANSYS Workbench, that is the advantage of automating from the CAD to FEM to fatigue, and also including the including the optimizations part. So we can do a CAD to FEM continuous seamless integration, and comprehensive fatigue analysis is possible. And we can also do a design optimization, that is by changing the parameter. You can see that what is the life variations. You can set the target life required. Typically, that I think this is a familiar process where we build the model and we set a parameter. Okay, these parameters are something like, for example, if you are having a shaft, let's say you have a shaft kind of thing, you have a radius, a length, and the material and other things. We can set that as a parameter in the option, and these parameter will work within the design modeler to change the model continuously, and that can be taken into a static structural analysis to perform the single cycle of the stress levels. Then you can take it to the ANSYS encode DesignLife. In the encode DesignLife, we will look into that, and there are multiple options are available to handle constant loading conditions. Then there is a EN based constant, EN based time series, SN based constant, SN based time series, vibrations, and so on. And all the parameter can be set again back to the optimization cycle, where you can have the design explorations, where it gives a better life, and or the what parameters are contributing to the life of the component. That can be done with a sensitivity analysis and so on. So the advantage here is you will be able to simulate from start to end the automation of complete fatigue, including the optimizations part. There are two sets of databases we will be seeing in the seeing in ANSYS Workbench with a standard material database. These are standard material database. Typically, you get from ANSYS engineering database. There is another set of the database can come from Granta. Granta is an material database, and for the when you are installed encode part, encode also gives you a material database with a very detailed fatigue the properties for the given material. Then once we bring the model, I think we will just get into the model. Once we bring it inside, there are multiple options you can see on the right hand side where you can see the input functions, the basic signal processing, design life calculation based on different aspects. This is the difference which makes from inbuilt fatigue code within the ANSYS and also the additional options which you can see here. And then the loads, the time histories you can apply and then perform the fatigue evaluation, where we will be first mapping the material and then we will map the load conditions and then we will map the, let's say, advanced settings where we will select like what should be the mean stress correction equations, what should be the stress values it should consider for calculating the fatigue life part. So this is the GUI of encode. And coming to further, so three inputs which will go to the encode design life. One is basically the experimental material data. The second one is the load histories. The third one is the FE results. So this will be taken from ANSYS Workbench automatically here, and then to the adding the time history and material selections will follow from here to here. So the material we select can be both are same. And you can have changes as well. So based on these three input, encode will compute the damage as well as the life required life of the component. And also you can this is a kind of a process automated where you can have, if you are evaluating a design or the fatigue evaluation criteria based on certain step, you can use the box, the available box, and build your own evaluation criteria within the encode environment. Once this is done, you can use it for SN curve based approach or EN curve based approach, stress approach or strain approach, and also damage calculations based on the safety factors. We can handle a thermomechanical. There is a short fiber composite fatigue is also available within the encode. And there are many components are being used from starting from a simple the consumer good to the biomedical to aerospace to other applications over the year. So with this, we can also have a cyclic symmetric component where you want to account the cyclic symmetry into account. You can consider that as well. Let's look into the model part. So I will just duplicate this to show you a quick analysis things. So when you open this ANSYS Workbench, you will also have encode installed on the same machine where additional options of analysis will be get added on the left hand side. You can see the encode EN constant design life, encode EN time series design life, encode EN SN constant and time series, then vibration SN vibration with PSD, then weld shell seam. Then there are other options of the things are there. So these are associated with the stress based life and strain based applications. I'm just. Yeah. So here, when I take it on engineering, the first thing is engineering data. When you click on engineering data, you may not have the encode data here. You can go to the data sources. The ANSYS working procedures remains the same. So here you can browse it, and typically the when you go to the C drive, you will have a encode installed. In the encode, you can open the encode GW and then go to the mats. In the mats, you can find the material data, gray iron and other thing. And there are number of material data. You can import this, open the data. It's already opened here. You can see that when you double click on it, you will be able to see the material properties. For different material, the database of encode provides the detailed strain life parameter, stress life parameters, and so on. And also you can integrate the Granta database And the granted database also has a lot of material properties in the ANSYS work, and it can be integrated with ANSYS Workbench. You can see that here there are different material properties are available, but it's not a limitation. You can add your own material property by adding a new material and changing the things as like we do for standard ANSYS Workbench. And here the database is there for the around 250 to 226 material, but around 4,000 is available with the Granta database. So you can just select the material and add to the your application model. Similarly, I'll just take mild steel here. You can just say that plus button, you can add it. So now come back to projects and then just refresh the project. You will be it is added to the engineering database here. And then you can open the geometry and see the geometry model. It is opening geometry model. A simple geometry is created here. And I will open the analysis model and show the things. You can apply different loads. Here the same load is applied. You can make it as if you don't, if in the analysis system, if you don't select it as a number of steps, if I add it 3, then in the encode, you can identify all the 3 as all the 3 loads individually. If I keep it 1 as a value, then it will be all the 3 will be combined load will be applied on in the steps will be considered. If I take it 1 and this is a downwards, then upwards, then the other load is taken into account. Just solve the case or update the results. Yeah, that's all we do in the Workbench. You can take any model like applying the load case. Once we have done this, then we need to let me first select the encode constant thing, drag and drop onto the solution. When you drag and drop onto the solutions, it will automatically connect with the previous model. And then you just go here, because once it is connected, you need to update the model such that it takes all the data which is required for the further process with the encode. And then you can open the solution. That is by clicking and encode DesignLife will open. And this is the GUI of the encode DesignLife. And where you can have a DesignLife, there is a studio where you can change the parameter. Material manager is there, where you can add the material database from the different material part, browse and add it. It will be automatically added onto the database part of it. Then there is a separate vibrational modeler manager is there. On the left hand, right hand side, if you look at, there are multiple options. You can introduce. One is the input. If you are using ASCII input or different kind of input, you can use this option. The other option is to go is insert here input to the glype or function displays output, whatever, depending on the things you can make it. And also you can make it a interactive run mode. Similarly, we have the functions which are like you want to manipulate the histogram or channel controls. All these parameters, time series, multi-column, the test splitter or test combinations you want to add it. So these are the additional features which will add more realistic calculations or realistic handling of the fatigue loads. Then we have a standard load solvers which will handle creep, the Dangvan models, EN based thing, SN based, safety factor, vibration, strain gauging. All the options are available as a standard. Then you can see the composite solver available. Then vibration profile designer, like if you have extreme response spectrum, shock response or other things, when you add insert from the input class, like for example, if I use a histogram, you can see that it get added to the canvas and then you can design from here. I'll just remove this. And this is a standard workflow which typically get added when you drag and drop from the Workbench part of it. You can also build the your own application, including the script and the MATLAB, and then there will be a super glyph options. There are display options are available, chart display, and depending on what kind of output you want to make it. It's about most pre-processing of the fatigue evaluations as well as the post-processing option for the fatigue part. Let's click on this display. You can observe here the model is already taken. I just hold a control button and you will be able to see the model I have considered here. And now the model is added to here. In this case, you can right click on the here and there is a edit material option, material mapping. And you can see the carbon steel or mild steel, whatever you want to use it. The earlier one we have used with the carbon steel option, unless I in the Workbench, I need to change that material to the respective material data. So I'll be using here with the carbon steel only, going for a default. So the material is updated. You can also see the view the assigned one. This is the properties of the material type, UTS, E, and then all the property, and also like you can R ratio circle, you can do it. If you have a tested data, you can bring the tested data directly. So this helps us in mapping the material. Once you map the material, edit the mapping, then goes with the load mapping. Here we are not using a time series. If you are using a time series, then it makes more sense, and where you can map it for the things. But you can see that all the three load cases, you will get single load cases in the Workbench if you make it as one step. If you are making it different steps, you can it will automatically display here with the different load cases. And also it is a constant load cases. You can have a time series added to that, or you can have a time step based options where the scaling factor can also be added for each of the load cases. And then you can constant amplitude is what I'm looking at now. Then you can also add a duty cycle. You can add a vibration loads. You can add a hybrid of them. You can add a rainflow counting based on that. So these are multiple options which you can use it for handling your load conditions. Just say OK. And then you click on the advanced edit option, where you can see that advanced edit options gives you various methods. For example, SN method we are using now. So under that also there are different things. You can refer all this, the Hague diagrams or other channels in the encode theory manual, which will give you a description of different SN methods are being added. Combination methods, you can use a maximum, absolute maximum principle, or one MISIS or maximum principle, shear, critical plane. There are different approaches are available here. In the same way, you can use the mean stress corrections options, where you can go with a Goodman, Gerber, or FKM, depending on what kind of model you're going. So we can just take a Goodman here. And also you can have a multi-axial, simple biaxiality or standard or auto. So I will leave most of these parameters as an default. And also, like I'm just showing all these options. It is when you go depending on your problem statement, and I think it will be a this window will change. And also you can change the parameter in the analysis group as well. So this is the whole detail of load mapping, sorry, advanced edit part. So because it's a, and one more thing I missed to show. Here you can see the surface nodes only. You can activate as false if you want to go for all. Fatigue is a surface phenomena. You can take it as true. If you are only, it will be quicker. So I'm using true as an option for the same. After this, I think the initial setup for a basic analysis is done. Then click on this button. It will run the analysis part. You can see the 0 completed entities and other cases. So just maximize this, hold a control button where you can rotate and see. There are different post-processing options are available. Because of time constraint, I'm just rushing through with this. Here you can see the damage levels, the static failures, and also you can put a band, double click on this. You will be able to see the results for different load cycles, depending on what load cycle you want to see, or load cases, the damage levels you want to evaluate. Or you can use it for all, or go to the result, which will add options for different options of the total average. And you also have a damage here, the life calculations, and you can also add your own calculation method, the biaxiality, then plane angle, maximum stress, minimum stress observed, all this. Let's take a life only. Damage you have seen, we will take the life options. There you can set the ranges, and also you can make a custom range. If you are looking at a component, how it is getting damaged within the desired cycle, or within the desired cycle, if it is passing, then what is the level of damage observed or life observed, you can click it. So when you click on it, you will be able to see the static failure plus the life added repeats. So this is the critical area where you get an different stress values. So this shows the workflow part of it. There are multiple options are available within like encode. So as I shown, using these histograms or the processing the basic function as the integration as well as your PSD data calculation, the strain Rosette models, rainflow counting models, the graph frequency spectrum handling, the force Fourier filters you're adding. So the options are more. This today's is just to introduce what options are available, why a simple workflow, and the next webinar we will be covering each one of these topics in detail.